Hi, I'm Mark.
Hi, this is Alan, and today we'll be using TDA to define college basketball positions with Mapper. Our presentation is divided into three sections. First, introduction to Mapper and the math behind it. Second, looking into the original paper we based our research on. And third, our findings. So visualizing high-dimensional data with Mapper. To summarize, given an input point cloud, Mapper reduces it into a simplicial complex with fewer points, which can then capture topological and geometric information at any given resolution. As seen on the circle right on the top right, in which points are colored based on their distance from the leftmost point, Mapper then breaks up the circle into overlapping slices. It then decomposes each slice into clusters, giving the colored vertices. Two vertices are connected by an edge if the clusters overlap, as Mapper is soft clustering. The graph on the bottom captures its shape.
So now looking at a three-dimensional example where we have the shape on the right. A brief introduction to the pipeline of Mapper is that it takes three different types of inputs. It takes a filter function, a clustering scheme, and it takes resolution parameters, which is the number of coverings we have or the number of intervals and how much those coverings overlap. If we look for a filter function F here, we have four different coverings of the data. And then we break that into the components in the pre-image. We use the connecting components here using some sort of clustering algorithm, and then we connect those connected components that overlap with different intervals. And we get the simplicial complex on the right, which captures some of the topology of our original shape, but fails to capture the bottom loop. So while Mapper is used to catch the general idea, definitely does miss some point of the original topology.
Now on to some strengths of using Mapper. Other dimensionality reduction methods such as PCA often suffers from projection loss. Instead, the pros of Mapper is that after choosing the lens, the covering in the projected space is pulled back to the original high dimensional space, then which clustering happens. So we see two Mapper graphs here. On the left, where red points correspond to ground truth fraud. On the right, the same Mapper graph is present with now red points corresponding to predicted fraud. This shows where the model misclassifies the fraud and characterizes errors according to which cluster of the Mapper graph they belong to, which can be used for predictions and classification problems. Instead of trying to determine the shape of the entire data set, Mapper can help compress the data into a form that can be easily visualized. It is important to note that the Mapper construction provides a coordination by the creation of the simplicial complex to which the dataset maps, and not by using real-valued coordinate functions.
Now to explain some of the TDA behind Mapper. So the nerve, recall from class that the nerve of a covering U, the simplicial complex NU, whose vertex set is in the index set A, where the family alpha 0 through alpha k is a k-simplex NU only if its coverings in the X set all intersect. So they have a non-empty intersection. And then given a space equipped with a continuous map, where Z is a parameter space that has a covering with A as an indexing set, F is continuous, and that's proved in the paper. If you want to reference our works cited. The pre-image of a covering forms an open covering in X. We consider now for every alpha in the decomposition of the pre-image of our coverings, until we look at them and we look at their connected components. And we can write the pre-image as the union of all the connected components in that covering. And then we call this U tilde, which is X obtained this way from our covering U. Let's look at an example of this. So say we have a circle. We break it up to three coverings, which is essentially the filter function takes the X values and we cover those X values, which is -1 to 2/3, -1/2 to 1/2, 2/3 to 1. And then we look at the pre-image of that. So we look at the leftmost part of a circle, that's one connected component. We look at the middle circle, -1/2 to 1/2. There's two components there. If we look at the right, there's one component. So we cluster those or break them up to their connected components. And we get the simplicial complex on the right by taking the nerve, which we connect over intersecting parts. And we get something that overall gives us the general idea of the geometry of a circle. There's one cycle, there's a whole routine, we've achieved our main goal.
So filter functions, just to recap Mapper, we apply a filter function to the high dimensional data, determine overlapping coverings based on that filter function, and cluster the preimage of the covering in the original data set to take the nerve of it. So the function chosen to partition the data set is very important for a mapper. And here are some few common examples that are used. First, density. Second, eccentricity. And another similar one is L infinity centrality, which is defined for a data point x to be the maximum distance from x to any other data point in the set. Large values of this function correspond to points that are far from the center of the data set.
And now let's look at clustering too. So in the simple examples we defined earlier, we use the number of connected components. But if we're looking at a point cloud, we don't have these connected components that are ideal. So we need to use some sort of clustering algorithms to divide up what we have in our coverings. And this is left up to implementation, which is an issue, obviously, because some of our visualization is going to be due to cherry picking a certain clustering algorithm, as well as a certain filter function that gives us the data that we want, the visualization we want. It doesn't give you an objective visualization of the data. So now let's talk about the motivation with basketball positions. Know that there are 5 traditional positions in basketball. There's the point guard, the shooting guard, the small forward, power forward, and the center. And the point guard archetype is a shorter, faster player that would be in the backcourt leading the plays, while the center defends the paint in the rim normally. However, as basketball has evolved, we've seen changes these positions, and we've seen the growth of this term positionless basketball. Teams can be employing multiple forwards or all guard lineups. And this idea has allowed certain teams to outrun others who don't adapt to that and don't have this dynamic playing style. And then furthermore, positions don't really reflect what their names say. So for example, Kevin Durant, who's 7 feet tall, when he came to NBA draft, actually reported his height as 6'9". So people marked him as a small forward rather than a center. Because while he had strengths and abilities that catered to being a small forward, he struggled in a center position. As a 7-footer, he hated being labeled as a big, and really raised the question: why not classify players by their skill sets, and with that, their statistics that reflect those skill sets? With this inefficiency of outdated and predefined positions, there's work to redefine them. Hence the use of TDA in basketball. Moved through Algapon, working with Ayazdi, a company that licensed TDA software, tackled this question. Instead of the 5 traditional positions, they found 13 new positions, including offensive ball handlers, 3-point rebounders, and even a one-of-a-kind all-star player. Now let's move on.
So Agapod constructed performance profiles for each of the 452 players in the NBA using the data from the 2010 to 2011 NBA season, with each player forming a point cloud. His clustering methods weren't specified in his paper. We used dbScan, and the filter functions were defined by primary and secondary SVD. On the left, we see a lower resolution map at 20 intervals for each filter, and on the right is a higher resolution map at 30 intervals for each filter. The overlap is such that each interval overlaps with half of the adjacent intervals, and the graphs are colored by points per game. We see the 13 positions on the right. And next slide, please. Algapon used metrics of rates per minute played of rebounds, assists, turnovers, steals, block shots, personal fouls, and points scored. The distance metric and filters used in the analysis were variance, normalized Euclidean, and principal and secondary SVD values as mentioned. And from these networks, we see a much different structure than the 5 traditional categories of positions we mentioned. As we can see on the higher resolution graph, we can see a finer stratification of guards into 3 groups. So instead of just a point guard, the shooting guard, we have offensive point guard, defensive point guard, and ball handling shooting guard, also a role playing guard. In others, we see 3 smaller structures in the lower part of the map, which are labeled All-Star NBA and All-NBA Second Team. So the All-NBA network consists of the NBA's best players, and the second NBA team also consists of players who are also all-around excellent players, but who might not be just as good as the top performing. And some examples are LeBron James, Kobe Bryant in those seasons. Um, so the two graphs are different in resolution, and comparing them can lead us to new conclusions. And so on the lower resolution, we see a general four categories of forming clusters, which is a scoring, big men, the guard, the paint protectors, and the role-playing point guards. And the high resolution gives us 13 different positions to work off.
So telling the story behind some of these data, Team A is the 2011 Dallas Mavericks, which ended up being the 2011 NBA champions, and Team B is the Minnesota Timberwolves from the 2011 season, team that wasn't very good, very far from being the NBA champions. Story with Team A is that in this season, the Miami Heat was formed. It's a super team NBA. Caused all this fuss. They were the villains of the NBA. The heroes that came for the Dallas Mavericks, led by Dirk Nowitzki on the tail end of his career, who is now only an All-NBA second team player, even though he previously was a first team player. And really what made the Mavericks so great was how their players bought into their specific roles and how they were all so specialized. So we can see that they had 3-point rebounders, they had ball handlers, they had shooting ball handlers, they had playing ball handlers, they had everyone who bought into a certain type of scheme and a certain role, and everyone was very specialized in their talents. Whereas Team B, while we have somewhat similar data, we don't have as much diversity in type of player, and we can see that they're somewhat top heavy. They relied on a player named Kevin Love to do most of their production. We have less specialization in the type of different ball handlers we have. Overall, team performed a lot worse. So now let's talk about our implementation. We replicated Algonquin's methods using college basketball player data from the 2011-2012 season, and we used 11 different metrics: points, minutes per game, offensive rating, usage rate, blocks, effective field goal percentage, true shooting percentage, total rebounds, defensive rebounds per game, assists, and three-pointers per game. Overall, these are just like common statistics used to quantify player production. And with these metrics, we use the Python Giotto-TDA library to actually implement the mapper algorithm. So let's look at what we got in that visualization. Something that looks very different from Algonquin's data, right? Algonquin's data has these very fine branches that come off, and they say hey, scoring bigs are going to be here, paint protectors are going to branch off here, offensive point guards are going to branch off here, defensive point guards are going to branch off there. For us, even though we actually had the same resolution parameters that Algonquin used in this finer image, you see much more something like the image A on the left, where you see this general overall round topology. It doesn't really tell us that much. It gives us these general roles. If we were going to try to do Algonquin on the right, we'd end up with something like this. End up with a one-of-a-kind players at the scoring bigs that branch off a little bit, 3.4s in the middle, all-around role players back there, so they're worse at everything. Playmaking guards over here, scoring guards the left. Regardless, the point is here is that these roles are a lot less clearly defined. And when we can try to place these labels, we really have less confidence saying these labels. And they mean a lot less because we have this much smoother topology. So let's talk about some of our takeaways from this image.
So we see less clearly defined roles with our topology graph, and it supports our original hypothesis and the common idea that college basketball is more, since it's more coaching system based, there's less specialization in the roles of players and the general roles each player fits into. So instead of the more specialized cycle, we have a large one cycle, and there's less talented players in college basketball compared to the NBA, which makes sense. So more bad players that can easily be grouped together is shown in our graph, and it just once again fits more into the traditional definition of positions.
Yeah. Continuing that idea, we go back to our image. It's important to note that it's hard to group these players on a filter function if they all are bad at everything, right? Let's put all the all-around role players. But using their statistics, another weakness of Algonquin's thing is that you end up having good players being defined as a position, right? All NBA first team is a position for him. All NBA second team, he says all-star second team. regardless, the good players end up being put in a certain category away from the rest. That's not really how positions should work. Positions should work based upon your strengths, but your strengths uh relative to who you are, not necessarily relative to what everyone else is doing. Um, and that's a little bit of the issue here with college basketball. There is more of just like a general position from bad players to good players. There's not as much players who are really good at one thing, really good at other things. There's some specialists that's much rare in college basketball than NBA, where the high octane environment forces players to really hone down on what they're good on. So let's talk about filter functions too. Talk about grouping good players and bad players. If we're gonna look at other filter functions that Giotto gives us, like eccentricity and entropy, you don't really get any meaningful data. You just get these chains where you have a good player and a bad player. There's no value in this topology at all. And if we're gonna expand on this project, we would code our own filter function that takes primary and secondary SVD values. That's exactly what Agafan did, given the constraints on this project. We didn't have time to do that. And changing which statistic we actually project onto using projection alters topology, but we get the same general idea, right? That college basketball is overall less specialized. We do not have these branching outs. We have so the positions within college basketball should be defined by what your coach says your position is and how you fit into a system. Because without players being less specialized, it's up to a coach to define where they should play, how they should play, what's going to work for the general basis of a team. And overall, what ends up happening in college basketball versus the NBA, which is much more player based. You let these talented players somewhat just do their thing.
Yep, and some limitations that from what Mark just said. So there's a lot of cherry picking in the parameters of methodology and filter functions and clustering methods. And so we looked for parameter values that gave a good trade-off between a number of flares and a small number of connected components. And we ended up with 20 intervals. And when using numbers of intervals smaller, the graph became too connected. And using higher number of intervals, it also took more time in our analysis, which could be looked into. And IAST, as mentioned, is a TDA company, evaluate around 500 million and keep a lot of their knowledge and methods to themselves, which is unfortunate. And the Giotto implementation of Mapper doesn't allow us to identify specific players in the simplicial complex, and that was a problem. The player's positions by Algopon's methods are also defined just by performance, and it could misrepresent underperforming players in certain categories.
Yeah. General idea also, including our limitations, that even though we came to the same conclusion that Algepon did, that 20 and 30 intervals are like the best two amount of intervals to have for your data. Um, that's essentially cherry picked, right? There's nothing that says like this is the correct topology, this is the wrong topology. We just get like a general visualization, we make a general conclusion. There's nothing super concrete. It's not even that much analysis that can be run on it. At least with basketball, it seems like you're putting these arbitrary labels on an arbitrary topology, and while you can make conclusions based off of that and say these are correct conclusions of the past, um, yeah, you're completely cherry picking what you're doing. That's the biggest limitation. Anyways, thank you for listening to our presentation, and
Thank you.
yeah, our works cited are here. If you want to reference any of that, have a good one.